this is a packet, the correct packet. So it arrives after 30 microseconds, and we can calculate the time of this packet, TD. Again, here we have to consider the propagation delay, transmission time in R2, propagation delay between R1 and R2, transmission time in R1, propagation delay between A and R1, and then you can see that the end of the transmission of D in A occurs after the transmission of 4 packets. So we have to consider 4 times the transmission time in A. It was 30 microseconds. Okay, and this should be 220 microseconds. Sorry? The time of E. I don't know why sometimes disappears.
0 plus 6 0 plus 6
Plus 6, yes. Yes, actually the result is correct. Okay, so now we have to consider the 2 packets that are generated in D and are going towards C, because they will cross the same path of the packets that are going towards B. And so we have to draw another line and let me also add some space here. Okay. For instance, we can use the green. And this is D, but not the receiving interface, but the transmission interface. Okay. So according to the text, this transmission interface starts generating the packets after a delay of 40 microseconds. And so we have to consider 4 squares. This is TD, it's 40 microseconds. At this time, it generates the 2 packets that are going towards C. And we have to consider the transmission from D, which is over link number 3. Okay? And link number 3 means that the transmission times takes 20 microseconds. So here we have the 2 packets that are going to C, C1 and C2. Okay. They propagate through link number 3 and they get to R2. Okay, so we can draw another line here. This is also representing R2, and the link here between the two is again link number 3. This means that the propagation delay is 30 microseconds. Okay. So C1 is entirely received in this moment, and C2 is entirely received in this moment. Now these C1 and C2 will be sent, retransmitted towards R3. However, we have also to take into account that also the packets that are going to B will be retransmitted on the same interface. So in this case, we have actually, we may have a queuing delay. Here it's not very simple, but so this is the time when B1 arrives to the interface. B1 arrives to the interface after 30, 60 plus 280 microseconds. No, okay, but then we have to consider that this is 80 microseconds is the time when B1 arrives to R1. Then B1 also has to be transmitted to R2. Okay, so the time when B1 arrives to R2 is actually this one. Okay, and then we have also B2 and then we will have also B3. Now we can notice that the packet C1 arrives to R2 exactly in the same moment when the packet B1 is arriving to R2. Okay. This is not a problem because they are arriving to on two different receiving interfaces, but then they will be they have to be transmitted together in the same on the same destination, which is R3. So there is a conflict between C1 and B1. They arrive exactly at the same time, so we can choose that one of the two is transmitted and the other one is remains in the queue, and we can freely choose which one of the two as we want. Okay, so let's say that we can decide that the packet that is going to C is transmitted first, and the packet that is going to B will be delayed. So now we have to consider the transmission. Let's use another color. Towards the next interface, which is the transmission towards R3. Okay, because the network, as you can see, is this one. Okay. So all the packets are in this interface and they have to be transmitted towards R3. the link that is connecting to R3 is link number 4. So let's say that we decided that the packet C1 is transmitted before and the packet B is delayed. How much does it take to transmit C1? It will take 60 microseconds. Okay. T4 is 60 microseconds. So this is the transmission of C1. Actually, C1 arrived, is the first one to arrive. Okay, so C1 is for sure transmitted as the first one. The ambiguity was between C2 and B1. Okay, so what I said about C1 actually applies to C2, so we can decide that C2 is transmitted afterward. And this means that B1 will be transmitted when the output interface is free, so it will be transmitted here. In the meantime, also the packet B2 has arrived to the interface in R2, so it will be transmitted right afterward. And also the packet D has been, the packet B3 has been completely received. Okay, so this is the time where C1 is received. This is when B1 and C2 are received. Then we have B2, which is received here, and B3 is received here. So B3 is put in the buffer, and it will be transmitted at this time. Okay. This is actually the most difficult part of the exercise. The other ones are. So now C1 and C2 and all these packets are going to R3, and actually this was so I need another line here. This represents still R2. This is was the receiver, and this is the transmitter. So this is channel number 4. Otherwise, it makes a lot of work. So after the transmission towards R3, we have to consider the propagation delay, which is number 4, 10 microseconds. So now we know the time when C1 and C2 arrive at R2. And finally, we are at the final steps. So from R2, the two packets that are going to C will go towards C, crossing link number 6. Okay. And what is the transmission time on link number 6? 80 microseconds. And the propagation delay is 0. So this is the transmission time of C2, C1, sorry. And then we have the transmission of C2. Okay. So now we can calculate the arrival time of C2. I do only the arrival time of C2. And here we have to consider 0 as propagation delay. Then here we have 8 microseconds for C2, which is transmitted after C1. So we have 2 times 8 so 80 microseconds. And then we have the propagation delay here, which is 10 microseconds. We have the transmission of C1 that was 60 microseconds. And the transmission of C1 started at this time. So we have to take another 30 microseconds of propagation delay. Plus transmission time here in D, which was 20 microseconds. And we have to consider TD, which was the delay, the initial delay, which is other 40 microseconds. This has to be multiplied by 10 and is in microseconds. And the result here is should be 320 microseconds. Okay. Now the last part, which I am skipping because it's quite easy, is the propagation of B1, B2 and B3 towards the final destination, which is B. So you have to draw another timeline which is regarding to B, and this transmission occurs over link number 7. Okay. And here, as a final result, I have computed the arrival time of B3 which should be 440 microseconds. You can check. So after this long chain of time diagrams, we can note that sometimes the arrival time of a packet is independent on the time it was transmitted at the beginning. For instance, these packets that are going to B were originated in A, but in order to be transmitted from R2, they had to wait C1 and C2. And So it's the time when C1 and C2 are transmitted that tells you when these packets are actually transmitted, because they face this queuing delay. Okay, questions? So now we can consider the next exercise. Which is this one. It's about switching Ethernet switches, and the description is a little bit long, but the concept is quite simple. So there is a network that is in a connection of switches that are connected from by point-to-point links, and all these switches are also connected to a set of stations through these broadcast networks. And initially the MAC tables of the switches are empty. We have to consider to show how these MAC tables start to get populated using the learning and forwarding mechanism according to the sequence of packets that are transmitted between source and destination stations. And the sequence is given here. So you have all the sequence of the packets, and the network remains as at the beginning until time equal to 6 time, so to 60. And then in the next part there are some stations that have been moved from their original position, so disconnected from their networks and connected in other networks. And we have to show what happens in this case to the packets that are transferred, okay, the frames that are transferred. So in order to solve this exercise, unfortunately we should always have a look at the network. So what I can try to do is to try to copy the network. Let's see if it's possible. I copy it close to the table. Oh, it's too small. Can make it small. Okay. It's more or less visible. And we have to follow what happens when we are sending the frames. So we can start from the first time frame. The first frame to be sent is from station A to station E. And so the frame leaves station A and arrives at first switch S2, and this is already precompiled. In switch S2, the frame gets into the switch through port number 3. Okay, so in the learning mechanism, the source address is associated to the port, so we have this new entry A3. Then switch S2 has to look at the destination. Destination is E, which is still unknown in switch 2. So switch 2 behaves as a hub and sends the frame in a broadcast on all the output ports. So for sure the frame also through port number 2 gets to switch number 3. Okay, so switch number 3 performs the learning process, and again it associates the source address to the incoming port, which is port number 3, and again behaves in a broadcast way, so it will send the frame to all the destinations, including this port number 2. From port number 2 the frame gets to switch number the S1. Okay. In switch S1 again we have the learning process. A is associated to port number 3, and switch S1 behaves again in a broadcast way, so that the frame will be replicated also to F and G. Okay. In this sequence, the frame for sure has arrived to the destination, which was E. So in this case, we have that the frame arrives. In the first part, where we don't move any station, all the frames always arrive to destination. There's no reason, because if there is no knowledge about the destination, there is the broadcast behavior that ensures that the frame will arrive. Okay. Then we have the second frame that is from G to D. Always you have to look at the map and follow the frame step by step. So G is located here below. So the first switch is S1, and we have the learning process. G associated to port number 1. D is still unknown, so we have again the broadcast behavior. So this frame will arrive to all the 3 switches. The second switch is S3, and here we have G associated to port number 2. The third switch is S2, G is associated to port number 2. Okay. Then we have a frame that is sent from A to G, and it starts in switch S2. In this case, G is known, is the destination. So first of all, we have the learning process. The learning process just confirms what was already learned in the previous step, and then the frame will be sent out of port number 2. In this case, the switch does not behave in a broadcast way, because we have the destination that is known, and so it will get to switch number 3. In switch number 3, again we have a confirmation of the position of A, and it will be sent out of port number 2. Port number 2 gets to switch number 1, again another confirmation, and it will get to the destination, which is G. Okay. Then we have next the next frames from D to A, and D is located close to switch number 3. So we start from here, and in switch number 3 we have the learning process of D, which is D port number 5. The destination in this case is known, is A, so the switch will send the frame only out of port number 3, where it will get to switch number S2. S2 makes the learning process of D, and then the frame will be sent to the destination A. In this case, the frame does not reach switch number 1. Okay, so switch number 1, in switch number 1 we have no changes. This frame is the broadcast address, so it will have to be sent to all the destinations, and it starts from H, So H is located here. So we have first S3, when we have the learning process of H. Then from S3 we are going to S2 and S1 as well. And here we have H2 and H3. Okay. Next frame from B to A. And so B is located here. And the frame gets to switch S2. Okay. So first of all, we have to make the learning process. So we associate B to port 3. And then what happens in this case? Here the destination is known, because A is known, and it's associated to the same port as the incoming port. So in this case, the frame is filtered. It is not sent anywhere, because the destination is already reached. Okay. So we have to just to write this entry in this line and no other entries. Then we have the frame F to G, and this is quite a similar situation. F is located here, so we have the learning process of F. And then the frame is sent to G, which is on another port, so it's not actually filtered, but is sent in a unicast way because G is known. So it does not reach to the other switches. Notice that even when the frame is dropped, like in this case, still we do the learning process before dropping the frame. So now things are more interesting, and we have the movement of the stations. So let me see if I can select the map. It's very strange. Okay. And so what happens in this situation? We have a first frame that is sent from A to G. Now A is here, and so the frame gets to switch S1. Now S1 becomes aware that A was moved because the frame that is generated by A now appears on a different port. So here we don't have the confirmation of the previous entry, but we have an update. And then the destination is G, but G is still seen as connected to port 1. So this frame is filtered, okay, because it gets into port 1 and it should be sent out in port 1. So the frame is filtered, it does not go anywhere else, and for sure it will not reach G. Okay, so this is a frame that is lost. Then we have G that is sending to A, and the situation is quite similar. Now G is located here, so the frame gets to S2. There is an update of information because now before G was connected to port 2, now it's port 3. And it should go to A, which is still seen as connected to port 3. So also in this case, the frame is filtered and it will get lost. FH, so F is placed here, it didn't change the position. First switch is S1, so we have a confirmation of learning process of F. And then we have H, which is at port 3. So the frame will get to S3. In S3, we have the learning process of F. And then the frame is sent towards port 1, because H is again still seen at port 1. So it will not reach the destination, because H is not connected anymore here. So also in this case is lost. Last, H to A. So it starts here. Now S3 learns that H has moved. So we have an update here. And then we have that the destination is A, which is still seen at port 3. So the frame is sent to S2. In S2 we have the learning process about H, which is just a confirmation. It's port 2 as before. And then the frame is sent to port 3, because A is again associated to port 3, so it will not get to A. It's lost as well. Okay. So once you learn the automatic procedure, these exercises are quite simple. So now we can move to this exercise, which is about ARQ. So we have an exchange of frames represented here between the two nodes A and B. And the ARQ system is go back N. We have some assumptions. A has always data to send. Okay? So this means that if you see an interruption in the transmission from A, it means that this is the effect of a window, transmission window. Instead, B will send frames only when it has something to send. So the frames that are represented here are actually these gaps actually are given by the fact that B has nothing to transmit, okay, to send in spirit. All the frames have the same transmission time. The transmission window of A and B are of constant in size. So here we are in likely layer 2, data link layer, when the transmission frames the windows don't change. And we know that the size of the window in B is 3 frames. We don't know the size of window in A, we have to figure it out. The link is bidirectional and symmetrical. There is a timeout, the definition of the timeout from both A and B, which is of 6 times the transmission time. Then frames are numbered as usual with the two fields NS and NR. NS is to number the frames in one direction, and R is to number the arcs in the other direction. So we have to complete the empty fields, so to write the numbers here, specifying the size of the transmission windows of A and B. So we have to calculate the size of the transmission window of A, and then we know that there is an error in this observation time frame, We don't know when there is this error, we have to figure it out, but we know that there is just one transmission error. We have also to display the transmission windows of A and B on the graph, okay, by writing this expression, which is the bottom NS and the top NS that can be transmitted. So we can start, of course, from the left side. Initially, we can assume that the transmission window of A starts from 0, and as well as the transmission window of B. We know the size of the transmission window of B, so since frames are numbered starting from 0, if the size is of 3 frames, it means that B can transmit frame number 0, number 1, and number 2. Okay. So this is the top, the transmission window in frame in B. We don't know the size of the transmission window of A, so for the moment let's avoid writing it. Now, however, we know that A has always something to transmit, as I mentioned before. So here there is a moment in which A stops transmitting, and likely it is because the transmission window does not allow further transmissions. So since frames that were transmitted in this first burst are frame 0, 1, 2, and 3, it means that the size of the transmission window of A is WA equal to 4. Okay. And it also means that here I can write this as the top of the transmission window. Then we have, we can also fill in the value of NR, because we know that when the first frame is transmitted, B has not sent anything. When the second frame is transmitted, B sent something but is not arrived, so we can write NR equal to 0 here. And this is also the same in this case. Okay? In this case, the transmission, the first frame that is sent from B is received completely before the transmission of the third frame, but not on time. Okay? So the frame is already in transmission when this is completed. So the first NR different from 0 will be this one. And it will be equal to 1 because the first frame has been transmitted correctly. So it means that A is waiting for frame number 1. Okay, frame number 0 is acknowledged. So now we know that A is stopping to transmit. In the meantime, B is receiving these frames 0, 1, 2, and 3. It should receive these frames. However, we see that here, in the first frame that is sent to B, from B to A, NR is equal to 1. Okay? This means that only frame number 0 was received correctly, and frame number 1 was not received. So now we know that the error is occurring on frame number 1, the transmission error. Okay? And it's the only one, so it's important information. And this is obviously frame number 1 that is sent from B, and this would be frame number 2. So what happens when this frame that is sent from B arrives to A? When it arrives to A, it makes the window shift of one position. Okay? So in this instant here, the window of A will be from 1 to 4, and this allows A to send frame number 4. Okay. And since we know that there was a single transmission error, for sure the frame number 0 and number 1 sent from B were received correctly in A. So here we can write 2, okay, that is acknowledging the first 2 frames. In this case, below here, NR will be equal to 1 again, because frame 1 that was lost has not been retransmitted yet. Okay. In the meanwhile, what happens to the frame that was not received correctly? We know that each time a frame has been transmitted, the transmitter starts counting for the timeout. Okay? And also we know that the timeout is 6 times the transmission time. So here we can start drawing a line which represents the timeout. 1, 2, 3, 4, 5. This is here. 4, 5, and 6. We know that in this instant the timeout has expired. Okay? As soon as the timeout expires, the transmitter starts retransmitting the frames. And since we are in the go back N case, all the frames that were transmitted in the original transmission window have to be retransmitted. So we start from frame number 1, frame number 2, 3, and 4. Okay. So this gap here is due to the fact that the timeout is expiring. What else? Here we have also to display the transmission window of B, and since at this time we receive the NR equal to 1 here, the transmission window B in this instant shifts on 1 position. Then we have here in meantime, while A is retransmitting these frames, it has to retransmit the frames identical, but with an updated value of NR, because in the meantime the second frame from B was received correctly. So here we have to write an NR equal to 3. Okay. Then when this frame arrives in B, here we have a new update of the transmission window. Also here we have an update of the transmission window that will go from 2 to 4, and here another update from 3 to 5. Okay. Then this transmission window does not change, and then we have the transmission of the further frame from B, which is with NS equal to 3, and what would be NR. Now B has received frame number 1 and frame number 2 correctly, so here NR will be equal to frame number 3. Okay. I don't have any other observation. In this way, the exercise is complete. There's some questions. Okay, so let's move on. This is a little bit long. This is about forwarding. We have a router, and we have the list of the interfaces with their addresses and net masks. And also for each interface there is a value of MTU, maximum transmission unit, that is defined. And this is instead the routing table of the switch is below, where we have 7 entries. The last one is the default routers, as you can see. So we have to consider a list of IP packets that is given here below. They arrive at the router, and then for each one we have the destination, IP address, the size, the value of the flag do not fragment. If the flag is equal to 1, it means that do not fragment is enforced. And we also have the ingress interface. We have to understand and to write how the router will forward the packets. So stating the type of forwarding. In case of indirect forwarding, we have to write down the line of the routing table which is matching, and the egress interface, and in case of dropping, why the packet is dropped. And then there is another question which is reported below, which is to rewrite this routing table in a compressed way. So when you have these exercises, it is quite useful to add another column to the table. In this other column we can write the output interface that is corresponding to these next stop addresses. Okay. All these next stop addresses are the addresses of interfaces of other routers connected to our router that we are considering on one of its interface. Okay, so here we have this. If this is router number 1, we will have another router here that can be next stop for some destinations, and this second router is connected to the interface, this interface of router number 1. So knowing the address of the interface that we have on the other side, we can understand what is the address of the network which is connecting the two routers. From the rest of the network, we can understand what is the address of the interface of the original router. For example, if you take the first line of the routing table, the next stop is 87.20.35.254, and this address clearly belongs to the network 87.20.35.58.0 with this net mask. Okay. So it means that this router, this next stop router, is connected to the interface ETH number 2. Okay. And the same obviously also for the other one. Then we have the third line, which is 11.0.124.3. We have to check it against this interface 11.0.1.6 255.255.0.0, and they are clearly matching. So this would be interface ATH1. Okay. Then we have this one, and here we have to check it against the first interface. Notice that the net mask in the first interface is 128, which is not exactly the multiple of an integer number of bytes. So here we have to check what is this net mask in binary, and it's 1 and the rest is 0. Okay. So it means that if we are matching, the last byte here should have the same value that 81 has in the first bit. So 81 is less than 128. So it means that here the first bit is 0. It will be .0 something. And this also is .0 something. So they are matching actually. This one. So I can write ETH 0. Then we have ETH 2. Here we have ETH 0 and ETH 0. Okay. Why you need this extra column? Because with this extra column you can easily check the conditions for packet dropping in terms of MTU, because you understand what is the interface, the output interface, and then you go to check. So now we can start looking at each packet. So the first one is this. It's 131.12.26.4, and again this is matching with the first interface, because for the reasons that I have explained before. So 4 means that the first bit here is 0, which is also 0 here, and so the forwarding type will be direct, because I am sending the packet directly out of this interface. However, the size is 210 bytes, interface is ATH1, and the MTU is 100, and also do not flag is set to 1. Okay. So in theory I should fragment the packet, but since we have do not flag, it means that I have to drop it. So the reason is that the size is larger than MTU, and D is equal to 1. So this packet will be dropped. Second packet, here we have 110.0.26.4. First we always have to check the packet against the interface addresses. Here we have no matching, clearly. So it means that this will be indirect in terms of forwarding, and we have to start looking in the routing table. It could match with the first line, but actually no, it's not possible, because in the first line the third byte here is 1 and here is 26. Okay, so for sure it doesn't match with the first line. We have to check for the second line. Okay. So here we have 255, 255, and 245 and 240 in terms of net mask. 240 means in binary 1, 1, 1, 4 ones and 4 zeros. So it means that the packet is matching only if the address is equal to the destination address up to the first 4 bits of the third byte. But here the destination address is has a 0, and in the packet we have a 26. Okay. 26, if you write it in a binary, is 0, 0, 0, 1, 1, 0, 1, 0. Okay, because it's 16 plus 8, which is 24 plus 2. Okay, and since here we have a net mask with 4 ones, so it means that the network prefix stops at this bit. There is no matching, because here we have 1, and in this case we have 0. Okay. So even if apparently it is matching line number 2, actually it is only matching line number 7, which is the default router. Line number 7 means that the egress interface is ETH0. So now we have to check. Here we have do not fragment, the size is 100, and if you go to ETH0, the size MTU is 100, so it's okay. So the packet is forwarded there. Then we have this 11.0.255.255. This is matching the interface number 1, ETH1. But we have a directed broadcast packet. Okay, because this is the broadcast address for that network. So the forwarding will be direct. Egress interface is ETH1. ETH1. MTU is 250. In any case, here do not fragment is set to 0, so we don't have to worry about that. So the packet will be forwarded, and in particular it will be forwarded in a broadcast mode. So it will be forwarded to all the stations that are connected to that network. Then we have this other packet. This is again matching with the same interface, so forwarding will be directed. We have a size of 210. Egress interface is again ETH1. Do not fragment is 1. And the MTU is 250, so it's okay. So the packet will be forwarded. And you can notice that the input interface is the same of the output interface. So in some cases, some routers are not allowing this bouncing of the frame, of the packet. So in some cases it may happen that the packet is dropped. So if you want, you can mention this. Okay. Next example, here we have this destination address. This is the limited broadcast. So in any case, a router that receives this packet will drop it, will not forward it in because it means that the packet was transmitted in a broadcast way, but it has to remain local in the same network. Then we have these other examples are quite easy. This is indirect. It matches number 7. ETH is equal to 0. Do not fragment is 0, so even if the size is large, we can send it, and it will be fragmented. You can specify also this. This is also indirect. It is matching row number 6. Egress interface is ATH0. And the final one is this one. Here we have 131.12.38.220, and we have to decide what is matching between line number 3 and line number 5, and also possibly the default router. So since we have in line number 3 we have 255 here, and it's 38, so in theory it can match. Here we have 248 as a net mask, and 248 means .1.11111 3 zeros. So it should match 216 with this net mask. And here we have a 58. And so since we have a 58, this is clearly not matching because we have oh sorry, it was the wrong line. 220. Okay, 220 is .110.11100, and it is actually not matching that line. Okay? So it's not matching line number 3. However, it's matching line number 5, because in line number 5 here we have a net mask which is 192. That means only 1 and the rest is 0. The first 2 bits of the destination address are equal to this one, 192. Okay. So the final one here is going to redirect row number 5 ETH 2, and we don't have a problem for the size. Okay. Now the last question is to rewrite the routing table in the most compact possible form. So it means that we have to look at the original routing table and see if we can apply route aggregation or super netting if you prefer. So let's go to the original routing table, and so the first condition to apply route aggregation is that the next stop value is exactly the same. Okay? Otherwise it means that the packets are going to different output interfaces, or to the same output interface but to a different next stop router, and you cannot merge the entries. And so in the case of the first two entries here, this condition is compliant because it's complied because the next stop interface is exactly the same, and moreover we can apply super netting, because if you can see the two network prefixes, they are the same up to a certain value. So what I can do is to replace these two lines with a single entry, which will be 110. I write it here because it's closer. 110.0.0.0, and then the net mask will be 255.240.0, and the next stop will be 87.20.35.254. Okay. Then we have to look at the other lines. For line number 3 and line number 5, we are in the condition of applying super netting, because the entry in line number 5 contains the prefix in line number 3, but as you can see the output interfaces are different. So in this case we can do no aggregation. Okay, so this will be copied the same. If you look at line number 5 and line number 2, here we have the same output, the same next stop address, but the network prefixes are not, you cannot do subnetting, also super netting with these prefixes. They are very different. Finally, we have this line, which remains. This is not cannot be. Oh, these two can be again. These two could be aggregated. Okay, because line number 6 contains line number 4, but in this case the output interface is the same, but the address of the next stop router are different, so you cannot do aggregation. However, we can do aggregation on these two entries. because in this case we have the same next hop address, obviously the same output interface, and the default router contains everything. Okay. So here we can do aggregation and we can use the default router directly. And this would be 3.12.6.1. Okay. So in the final routing table, you can write 1, 2, 3, 4, and 5 entries instead of the original 7 entries that we have. Okay. Questions? Okay, so this is the end of the exercises. As you can see, each exercise has a maximum number of points. For instance, this has 6 points, and the others, according to the difficulty of the exercise, the maximum value changes. However, I also apply some, say, adaptive scoring. If an exercise was done by nobody, for instance, because it was too difficult, I will decrease its weight into the final. So then there are the theoretical questions. Usually I do 4 questions, and each question will be 2 points. So in the total you have 8 points on this part. And let me make some space. Okay. So the first one is dedicated to DNS, symbolic name resolution. We have to show the difference between the recursive and in the iterative mode, and to draw, to display graphically 2 situations in order to compare the 2 cases by using all the components with the appropriate name in the DNS database terminology. So this is actually what you find also in the slides. You have this is the iterative case, and the basic components are the client, which is making a request to the DNS database. The client is always interacting with the local DNS server. This is the requesting client. And then we have the root DNS server. We have the top level domain DNS server, and at a certain point we have the authoritative DNS server, where we have informations about the target, okay, which is let's say the server or the host that has a certain symbolic name and this host will have a certain IP address. Okay, let's call it IPE. So the local DNS server receives a request from the client. In the request we have the symbolic name, that we want to resolve. Then the local DNS server will start querying the root DNS server, and in the iterative case, the root DNS server directly responds to the local DNS server by sending the name, the symbolic name, and the IP address of the top level domain server that is appropriate to solve the query. In this case, it will be the top level domain server that corresponds to IT.it. And let's say that it has an IP address which is IPB. So here you will have .it and IPB. Then the local DNS can query the appropriate top level domain. Top level domain will answer by providing the name of the authoritative server, that in this case would be polimi.it with an IP address, say C. So here we will have IPC in the reply, and then we have the final query. And the authoritative DNS will answer by sending IPE, which is what the local DNS server was looking for, and the local DNS server will return the response to the client. Okay. This is the iterative mode, and we have the recursive. Okay, don't repeat all the names, you have to write them. So this is the local DNS server. The local DNS server will query the root will query the top level domain, the top level domain query the authoritative, and then we have the back propagation of the answer through all the path, okay, directly back to the local DNS. And here it will contain, all these messages will contain the IP address of the target. Okay. Second question. The difference between HTTP/1.0 non-persistent, HTTP 1.1 persistent with no pipelining, HTTP 1.1 with pipelining, HTTP/2. And we have to show the differences considering a practical case when we are transferring three different objects with different size. So first case is HTTP/1.0 non-persistent and also with no pipeline. What happens in this case? We have to open a connection. This is the client and this is the server. So first we have to open a connection. We have to send a GET. And the first object is retrieved. The connection is closed, so we have to open again the connection, send another GET, get the second object, this one, open again the connection, get the third object. Okay. Then we have the persistent, so HTTP 1.1 persistent with no pipeline. So the only change is that we open the connection only once and the connection remains open. So we have to send the GET, get the first object, send another GET after we have received the first object, and we will get the second object, send another GET, and get the third object. Okay. Then HTTP 1.1 persistent with pipeline. Open the connection and then we send the first GET, and while the server is sending the first object, the client can send a second GET. When the server finished to send the first object, it immediately starts sending the third. Meanwhile, the client is sending a third GET, and so the third object will be delivered immediately after. Okay. The quality of the pictures are not very nice. Finally, we have the HTTP 2 case. So we open the connection, we send the first GET, and here we can divide the object in chunks. Okay. So for instance, I can try to divide the first object in 2 chunks. And after the first chunk of the first object has been sent, we can receive the first chunk of the third object, or the second object, and then the chunk of the third object. Okay. Then there will be another chunk of the first and other 2 chunks of the big one. What is the advantage? Is that we have immediately a first chunk of each object. So, for example, if this contains information to show a specific graphical page, we can start showing the main graphical elements, and then as the other chunks arrives, the details get more defined. Okay. But you can view the entire page immediately, even if it's not in the full details. Obviously, the total time here should be equal to this time. Just the picture is difficult, but should be equal. Next exercise. Consider a slotted ALOA network. We know that on average 5 frames are transmitted, including retransmissions, for each frame that is successfully delivered to the destination. We have to compute the throughput and the total traffic. So this is basically the same exercise that we have also seen during the classes. We have to remember the formula of the throughput in the ALOA case. Here we are in the slotted ALOA case. So it means that the throughput S, if we have to consider, of course, the assumption of an infinite number of stations. So the throughput S is given by G times G power minus G. Okay. And then we know from the text here that we have 5 frames transmitted for each frame that is successfully delivered. So it means that G is equal to 5 times S. Okay, because to successfully transmit 1 frame, I have to send a total of 5 frames on average. So here means that we can write that G divided by S is equal to 5. And from here we can write that G divided by S is equal to E power G plus G. So if you put these together, you have that 5 is equal to E to G. So it means that G is the logarithm of 5, which is approximately 1.61. So if you replace G in one of the second equation, S, that is G divided by 5, will be approximately equal to 0.32. Okay. And here you can, for example, mention that in the slotted ALOA case, the maximum of S is equal to 0.368 in case when G is equal to 1. So it means that in this system we are almost at the maximum of the throughput. Okay. So we have overcome G, the best value of G, so we are overloading the system, and the throughput is a little bit less than the maximum possible. So if you are considering the behavior, it means that we are in a point area there. Last is very simple. What are the private IP addresses? As you know, they are addresses that can only be used in a private environment because they can be reused on several interfaces over internet. And so the condition is that packets that are sent having these addresses as a source or a destination can never get out of these private environments, that are called the private realms. And there are actually 3 blocks. Here you can just mention one if you don't remember all, but they are quite well known. The first one is this, and this corresponds to one network in class A. Then there is a second block, that is this one, uh, 31. These are 16 networks in class B. And then there is a third block which starts with 192.168.0.0 until 192.168.255.255, which is the equivalent of 256 blocks of class C. Okay. Questions? Doubts?